You have this amazing paper you co-authored, a survey paper called Emergent Abilities of Large Language Models. It has, again, the philosophy here that I'd love to ask you about. What's the intuition about the phenomena of emergence in neural networks, transformers, language models? Is there a magic threshold beyond which we start to see certain performance? And is that different from task to task? Is that us humans just being poetic and romantic? Or is there literally some level at which we start to see breakthrough performance?
Yeah, I mean, this is a property that we start seeing in systems that actually tend to be. So in machine learning, traditionally, again, going to benchmarks, I mean, if you have some input output, right, like that is just a single input and a single output, you generally, when you train these systems, you see reasonably smooth curves when you analyze how much the data set size affects the performance, or how the model size affects the performance, or how much how long you train the system for affects the performance, right? So, if we think of ImageNet, like the training curves look fairly smooth and predictable in a way, and I would say that's probably because of it's kind of a one hop reasoning task, right? It's like, here is an input, and you think for a few milliseconds or 100 milliseconds, 300 as a human, and then you tell me, yeah, there's an alpaca in this image. So in language, we are seeing benchmarks that require more pondering and more thought in a way, right? This is just kind of you need to look for some subtleties that it involves inputs that you might think of, or even if the input is a sentence describing a mathematical problem, there is a bit more processing required as a human and more introspection. So I think how these benchmarks work means that there is actually a threshold. Just going back to how transformers work in this way of querying for the right questions to get the right answers, that might mean that performance becomes random until the right question is asked by the querying system of a transformer or of a language model like a transformer. And then only then you might start seeing performance going from random to non-random. And this is more empirical. There's no formalism or theory behind this yet, although it might be quite important. But we're seeing these phase transitions of random performance and until some, let's say, scale of a model, and then it goes beyond that. And it might be that you need to fit a few low order bits of thought before you can make progress on the whole task. And if you could measure actually those breakdown of the task, maybe you would see more smooth. Oh, like, yeah, these, once you get these and these and these and these and these, then you start making progress in the task. But it's somehow a bit annoying, because then it means that certain questions we might ask about architectures possibly can only be done at certain scale. And one thing that conversely I've seen great progress on in the last couple of years is this notion of science of deep learning and science of scale in particular, right? So on the negative is that there's some benchmarks for which progress might need to be measured at minimum at certain scale until you see then what details of the model matter to make that performance better, right? So that's a bit of a con. But what we've also seen is that you can sort of empirically analyze behavior of models at scales that are smaller, right? So let's say, to put an example, we had this chinchilla paper that revised the so-called scaling laws of models. And that whole study is done at a reasonably small scale, right? That maybe hundreds of millions up to 1 billion parameters. And then the cool thing is that you create some laws, right? Some trends, right? You extract trends from data that you see, okay, like it looks like the amount of data required to train now a 10x larger model would be this. And these laws, so far, these extrapolations have helped us save compute and just get to a better place in terms of the science of how should we run these models at scale, how much data, how much depth, and all sorts of questions we start asking, extrapolating from a small scale. But then this emergence is sadly that not everything can be extrapolated from scale depending on the benchmark, and maybe the harder benchmarks are not so good for extracting these laws. But we have a variety of benchmarks at least.
So I wonder to which degree the threshold, the phase shift scale is a function of the benchmark. So some of the science of scale might be engineering benchmarks where that threshold is low. Sort of taking a main benchmark and reducing it somehow, where the essential difficulty is left, but the scale at which the emergence happens is lower, just for the science aspect of it versus the actual real world aspect.
Yeah, so luckily we have quite a few benchmarks, some of which are simpler, or maybe they're more like, I think people might call these systems 1 versus systems 2 style.
Yes.
So I think what we're not seeing, luckily, is that extrapolations from maybe slightly more smooth or simpler benchmarks are translating to the harder ones. But that is not to say that this extrapolation will hit its limits. And when it does, then how much we scale or how we scale will sadly be a bit suboptimal until we find better laws, right? And these laws, again, are very empirical laws. They're not like physical laws of models, although I wish there would be better theory about these things as well. But so far, I would say empirical theory, as I call it, is way ahead than actual theory of machine learning.